next phase of the class that we're going to transition to now, which is the roundtable. And for the orbit transit and landing roundtable, I'm excited to introduce our next two guests. So first I'll introduce Ryan Watkins. Ryan is a program scientist in the Exploration Science and Strategy Integration Office at NASA. She's just moved over to NASA HQ. Congratulations, Ryan, on the really exciting new position. And for quite a while before that, she's also spent quite a lot of time looking at lunar landing sites, dust plumes, a lot of different considerations about preparing to land on the surface of the moon through her work at the Planetary Science Institute. And we also are joined by Phil Metzger, who is a planetary scientist at the University of Central Florida. He is co-founder of NASA KSC SwampWorks. We've been thrilled to host Phil before here at MIT at Beyond the Cradle, so he's coming back to MIT, and I'm sure you've been in and out with other groups since then, Phil, but it's great to have you back. And Phil brings expertise in developing technology for lunar resource extraction, developing and characterizing lunar regolith and regoliths and simulants from other planetary contexts as well. And I'm sure he'll have a lot to tell you about different landing considerations and the lunar mission architectures that he works on. So with that, thank you again, Kevin, so much for a great introduction overall for the class for these GNC considerations for landing. And now I'm going to pass it first to Ryan and then to Phil to introduce themselves with some short slides, and we'll transition into the roundtable discussion.
Yeah, so again, thanks for the introductions. It's really great to be here. And I see Phil's on, so there may be a little bit of overlap between what we talk about because we've worked closely together over the years. So I was just going to briefly tell you a little bit about my work looking at plume surface interactions on the moon, specifically how rocket exhaust interacts with the regolith during landing. I've also have a lot of experience in things like landing site selection. I am working as Ariel said, at NASA headquarters in the SEO office with the CLIPS program. So if you have any questions related to commercial programs, I'm happy to answer those as well. But my slides will focus on plume surface interactions. So again, I don't know what you talked about before I came on, and you may be aware of some of this, but during the powered landing of spacecraft on the moon, rocket exhaust plumes interact with the surface, and this alters the physical state of the landing area, also creates potential hazards to both the spacecraft and any nearby hardware that you may have. And effects of, I'm going to abbreviate this to PSI, the effects of PSI may differ depending on things like, the planet's gravity, the mass and thrust of the spacecraft, the physical properties of the surface, et cetera. And so this slide here, I'm showing a couple of things. First, I'm showing some orbital images from LRO of the Apollo, Luna, and Surveyor spacecraft. And here I've outlined what we call the blast zones. So these are the areas that were affected by rocket exhaust. They show up as photometric anomalies at the landing sites. And then the image here is of Buzz Aldrin standing by the Apollo 11 lunar module. And you can see kind of this area of increased brightness behind him and smoothing from the plume effects, as well as an area that's kind of darker and roughed up from the astronaut boot prints. So with all this renewed interest in the lunar surface and missions back to the moon, we really need to be aware of these exhaust plume interactions and the kind of the physical changes that occur at the landing sites, as well as the potential hazards that they cause. So just a couple of kind of bullet point real quick facts on PSI. For small to mid-sized landers, especially plume effects on the moon, they don't result in a crater. We're not blowing enough dust away to really kind of produce a new crater. They generally begin about 30 to 40 meters above the surface and creates a dust sheet that obscures visibility. The frames you're seeing here are from Apollo 15, and you can see kind of as the lander gets closer to the surface, the dust plume becomes really thick, and it's very hard to see kind of the hazards beneath the spacecraft. And the last one is the kind of clearing stage after landing, so you can see that the dust dissipates. The dust sheets typically blow about 0 to 3 degrees above horizon. Phil did a lot of work figuring that out, so I'm sure if you want to talk more about how we figured that out, he could tell you about that. Particle velocities tend to reach about 3 kilometers per second and can even reach escape velocity. So again, these are moving very fast and create a hazard for, again, nearby hardware. A lot of the work I've done has been looking at physical changes within the blast zone. So what actually happened on the surface during these effects. And so for some of the things that we've pulled out from this are that there's smoothing that occurs, like you saw in the previous image. Possibly fine particle redistributions. This could cause a brightening effect like we see in orbital images, as well as a destruction of fine scale surface structure. So there's this kind of fairy castle structure, we call it on the moon, where grains are supported by electrostatics. So you get these really fine like they look like castles, very castle structures. And this is destroyed by the plume effects, which then causes the surface to appear more reflective. I'm actually going to skip this slide because I could spend probably too long talking about it, and I only have 5 minutes. But if you want to come back to this, I can later, just explaining kind of some of the effects of what happens during landing with the plume and the regolith. But a couple of things I wanted to hit on real quick were the operational and environmental impacts, specifically the hardware damage. Like I mentioned, this is really well represented by Surveyor 3, which provides the best evidence of rocket exhaust plume damage that can occur during a spacecraft landing. So this Apollo 12 landed about 155 meters to the west of Surveyor 3. The astronauts returned parts of the spacecraft for analysis on Earth. And studying these pieces have shown that Surveyor 3, the surfaces on the Surveyor 3 spacecraft experienced pitting and cracking as a result of exposure to blowing dust from Apollo 12. And Surveyor 3 was actually positioned kind of below the main spray of dust from Apollo 12 because it was in a crater. So had it been directly exposed, this damage could have been much worse. You also get other operational impacts from things like engine configurations that could cause gas and dust to be redirected up towards your lander. Environmental impacts includes things like morphological changes at the landing site, changes in grain size, like I mentioned. And these regolith changes actually can extend up to hundreds of meters from the spacecraft. So this really elevates your need for surface mobility, especially if you want to get pristine samples. There's also some concerns with the injection of volatiles from the exhaust gases itself into the local environment. And just really quickly, I've looked at the blast zone area versus lander dry mass for all of the different missions, Surveyor, Luna, and Apollo, and plotted this relationship between the dry mass of the lander and the actual aerial extent of effects that you'll see from the plume effects. And so this relationship is really useful for predicting for future missions. And just for context, the HLS landers that have been proposed are way up off this slide. So there's going to be quite a bit of plume effects to consider for that. And just finally, a couple of mitigation techniques that have been considered include physical structures such as launch and landing pads. These could be created by things like sintering, regolith brick construction, deployable structures that you bring on landing, et cetera. There's a lot of different things being considered here, as well as things like berms or kind of regolith walls or inflatable structures that could deflect some of the plume effects. And then other considerations that we have to keep in mind are things like propellants. Some may be more suitable than others in situations where contamination of measurements by gases is a concern. We actually have one example, the SEAL instrument on one of the upcoming CLIPS missions that's going to actually measure spacecraft exhaust at the landing site to help kind of address this question. And I'll stop there because I know I've been talking for a while and hand it over to Phil.
This was actually a talk I gave at a workshop on lunar construction. Let me get into presenter mode. Okay, so I'm going to skip over the plume stuff. Ryan showed the pictures of the Surveyor, the cracking and the pitting that occurred from particles hitting the paint. I've got a video I want to show. This is a simulation using our best available model. The very light circle is the moon, and it's upside down from our perspective. So this is the south pole of the moon. And if a 40-ton lander landed right here on the south pole, the ejecta shoots out both directions. This is sped way up. This is actually like a several-hour video. But this is the ejecta sheet that blows out from the lander. So you can see it goes globally around the moon, and it continues to rain in for days. But the flux is extremely low after you get far enough away. So let me go to the next video. Here's the ellipse is the orbit of the proposed NASA Lunar Orbital Gateway. And so you can see this ejecta sheet crosses the orbit of that spacecraft. Now the impact velocities aren't that bad up here because the orbital velocity is very low. So these are not hypervelocity impacts for a spacecraft at this altitude, but still it will cause some abrasion and pitting on the hardware. Okay, so how far away can you land? This is data we did for the Google Lunar X Prize. This circle, this is the amount of damage that occurs. I'm just gonna leave it a qualitative scale for now, but these are different simulations. This is the benchmark we've got for the Surveyor spacecraft, which is a 5-ton vehicle, 8.5-ton lunar module landing. So it scales appropriately to the other data that we did. And if you say that 1% damage is acceptable, 1% of surveyors' damage is acceptable, and then you want to use up 1/20th of your damage budget per landing, that means you're going to have to land 26 kilometers away from your outpost. And so that's not acceptable. We have to land closer than that. So I did some work on how do you build landing pads for the moon. This would be for a 40-ton vehicle. This was some work I did for JPL in 2018. There's an inner zone that has to be very hot to handle the rocket exhaust, the stagnation region. There's an outer zone that has to just resist erosion. You need to do some site preparation, grading, boulder removal, compaction. There's been a lot of progress working with Caterpillar and other companies to develop autonomy to do bulldozing. So I did a trade study of all the different methods that we could think of for building landing pads, and tried to quantify everything in terms of energy requirements, mass of hardware, mass of consumables you have to bring to the moon, and the construction time. I won't go over all the numbers. After you do the site preparation, there are a lot of different ways you could build a landing pad. You could do solar sintering. Solar sintering doesn't really work too well because there's no depth of penetration for that wavelength. And so you end up building a thin crust. You could maybe build it up additively, but that'll take more time. And then there's issues of driving over the same spot. I don't want to go through all the issues. It needs a lot of work to make that work. Infrared sintering, using a simple toaster coil to heat the soil, that works too, but again, the depth of penetration isn't much. You've got to do additive building. We fired a rocket plume on one of these that was built on a volcano, and it just delaminated the sinter. It didn't work too well, so that would need more technology development. Microwave sintering works really well because the long wavelength gives you good depth of penetration. There's issues with process control, and it's a huge amount of energy. So when you when you look at the amount of energy it'll take to build a landing pad in a reasonable amount of time, it'll basically use up the entire energy source of your outpost for about 250 days. So you won't be able to do anything else on the moon while you're building the landing pad. Another approach is pavers. It's vastly more energy efficient to build pavers in an oven. But then you need robotic complexity to link them together, and then the gas gets through the cracks and the gas pressure builds up under the pad and explodes your landing pad. We have experience with that. So we've done scaling of the paver problem. Gravel and rocks. Paul Van Cesante at Michigan Tech has been innovating this. Your central region has to be impermeable, but you could stack up rocks in the outer region. You need robotic complexity, you need rock sorting, so we take that into account in the trade study. Polymer, you could bring polymer from Earth and simply spray it into the soil. It will break down in the hot region, so you need a high temperature polymer and you need to do maintenance and fix it every time. So then finally the trade study. Here's the results. I'll go right to the picture. Let me show this first. Additional considerations. The mass of the power systems. It's not just the amount of energy used, but the mass of those energy systems. There's a chicken and egg problem. How do you land the power systems on the moon before you have built the landing pad? There's a reliability issue. Avoid more complicated processes like gravel raking and sorting and laying gravel maybe. And so maybe we need to build a phase 1 landing pad, and then you can deliver more hardware and then build a phase 2 landing pad. So here's the result. The inner zone, you could do polymer, sintering, pavers. Is that all? Polymer, sintering, and pavers. Okay, for the outer zone, then gravel, polymer, and sintering, or pavers. So when you look at the combinations, these are the ones that make the most sense. Either sintering or pavers in the inner zone, polymer and gravel on the outer zone. So anyways, the bottom line is there needs to be a lot of technology work to be done on this. And that's where we are so far today. So hopefully we'll have a good discussion about this.
Fantastic. You guys have just provided a very efficient introduction to huge bodies of work that you're both leading. So thank you very much for that. We'd like to open it up now to the class for questions, or also to Jeff, if you'd like to ask an opening question for the roundtable discussion. We'll now open it up to a conversation. And you guys don't have to raise your hands. I know sometimes you've been raising the little yellow Zoom hand. You're welcome to just unmute and discuss. And if no one's immediately jumping, I have a few questions.
I'll start with I know it's always hard to ask the first question, so hopefully this will encourage people, the students in the class. But, you know, clearly Earth moving is going to be critical. Are you aware of any CLIPS payloads that are going to experiment with, you know, Earth moving? You know, you gave some figures for the amount of energy that it'll take to have a robotic bulldozer, but we've never actually done it on the moon. So that would seem to me to be an interesting, you know, research payload, is actually building a smaller model of a bulldozer and seeing what it really takes to command that robotically.
So I can take this one since I'm working with the CLIPS payloads. The short answer is no. At the moment, there are no payloads doing anything quite like that. We do have our first ISRU demonstration, in situ resource utilization demonstration, going up on one of the task orders, but it's more of like a drill that we'll be kind of drilling and bringing up some regolith and then measuring different elements in it. So yes, at the moment, no. That would be kind of maybe a more of a next level type CLIPS payload. It'd be really great to have some more demonstrations like that. Most of our payloads at the moment are just stationary. They're on landers. They're, you know, kind of mounted up, or their cameras. We do have one that has a small micro rover, but it's not really got any capabilities like that. So we also have a few calls coming out for more science payloads. I don't know if kind of ISRU things will fit in that, but it'd be really interesting to see if maybe we are hoping to get some more interest from kind of like the science technology mission directorate side of things. And it'd be really neat if we could get some more, some demos kind of like that. So yes, at the moment, no, but working towards that.
I'd say this is an interesting opportunity for any of the students in the class who may not have 100% nailed down your mission concepts. Potentially designing a mission idea around a bulldozer of some sort, or building landing pads, could be an interesting idea to include. Or even if you've already passed that stage, but you are proposing a habitat concept or something in your mission concepts, being able to point to this as an example of requirements of technology that need to be built up for the success of your mission. Something just to note. Other questions?
One question I was wondering, so Dr. Metzger, you mentioned that the flux of the regolith plume goes down significantly with distance. Do you have any sense of how quickly it might go down to, I guess, survivable levels for hardware over long duration? Like, if you know, ignoring the potential contamination of other sites and the issue of volatiles and all that, is a feasible option to have spacecraft simply land a distance away from the base camp, or would the distance necessary be too far for like repeated use?
Yeah, so that's a good question. And in the slides I said 26 kilometers, that was an estimate for a 8.5-ton lander, which is actually lighter than the vehicles that we're planning for Artemis. So the distance is too far. You really can't rely on just longer landing distance. But you could harden the assets on the moon. You could design them to withstand the ejecta spray. Maybe close off windows to optics, maybe deploy umbrellas or something before the landing. But to do that, we have to have international coordination. You know, the Outer Space Treaty says do no harm to other nations' assets. And if we want to be able to share the space on the moon and not end up carving up the moon with gigantic regions to keep each other out, then we have to have some sort of international agreements on how much damage we can cause to each other's vehicles. And we have to have coordination on when landings are going to occur so that nations can prepare their hardware for the events. Now, the damage is not that bad when you're at a distance, you know, but if you're talking about sensitive equipment, then it may be unacceptable. If you're within 10 kilometers, the damage could be really bad. But it's a systems engineering question. It really depends on the designer of the hardware, what they believe is acceptable.
I know that both of you are tackling these interesting standards questions. And Phil, I know you've participated in some of the Moon Dialogues, Open Lunar work, as I recall, some of the policy work to try to get some of these questions answered. What is both of yours take on current standards setting? Is there momentum towards standardization, at least among the CLIPS providers? So within our own country, within NASA's program, within those groups, are we starting to see some discussion about interoperability and standards for the surface of the moon? And then, Phil's alluding to the fact that it's a much bigger challenge to get this happening at an international level. But I would love to hear what you guys both think about standards and interoperability that's critically needed.
Yeah, this is a little bit of a hard question to answer. So yes, the discussions are happening. I would say, especially, I mean, going a little bit back in time, I was Phil's intern. And I remember when I was still an intern, kind of, we were putting out a big push for like, hey guys, this is an issue, like, please recognize it. And I would say we're kind of at the point where people recognize this is an issue and they're talking about it. In terms of standards, that's a bit difficult, especially on the CLIPS side, because these are all, they're independent businesses, and NASA can only kind of regulate what they do to some degree. That being said, we are working on discussions of things like interoperability, like you mentioned, for Artemis and for CLIPS providers. Now, NASA, right, like at the moment, we're not going to them and saying, hey, you have to, consider this or take these measurements or do these things. But we are actually flying several payloads on CLIPS missions that are going to be directly measuring plume effects. We're working out things like, we call them data buys. So can NASA buy data from the providers to get the kind of data we need to better understand these. So there's not really a standard, but there is a lot of progress being made towards understanding the problem and recognizing the problem.
I'll just add that there's an attorney, Michelle Hanlon, who has a nonprofit called For All Moonkind. Her focus is trying to get international recognition to protect the heritage sites on the moon. And so we've been working for a while on the plume issues, and she's become very focused on that in particular. But she doesn't focus just on that. She wants to do more preservation than that. So, but the reason she's doing this is there's a problem that the international law that allows you to nominate heritage sites for protection has a problem that it's impossible to nominate anything on the moon, because only the nation that contains the hardware is allowed to nominate it. And since nobody owns the moon, nobody can nominate it. So she's trying to work with the international community through the United Nations to fix that. But she has permanent observer status on the Committee for the Peaceful Uses of Outer Space, I think. And so she's been talking this at the United Nations level, saying that we need to have some sort of international framework to agree on how to manage plume effects. I mean, here's the fundamental issue. It's an airless body. So we don't have a lot of common sense for airless bodies. All of our common sense is based on a thick atmosphere where small dust gets stopped by the drag force of the atmosphere. And so if you take a handful of gravel, rocks, and dust and sand and throw it, the stuff that goes the farthest are the rocks. And then the sand goes the medium distance and the dust doesn't go any distance at all. But on the moon, it's the exact opposite. The rocks go the least, the sand goes the next, and the dust goes the farthest. And it's the most abrasive at a long distance. So it's an airless body with low gravity, but still enough gravity that you need to have a significant rocket thrust to land on it. And so that's the source of the problem here. And the international community needs to get our head wrapped around the fact that we've got to deal with this situation.
Phil, this is Jeff Hoffman again. Has anyone done calculations on, suppose you have berms, but you don't have a prepared landing site. So a lot of the exhaust is deflected, upwards. How would that affect the moon-wide distribution of the ejecta?
Yeah, so berms have been one of the things we've studied from the very beginning. We've actually had robots out at Desert Rats in the 2010 period building berms. I think they're important, and we probably should plan to build berms, but I don't think they're a complete solution for a couple of reasons. First of all, because if the berm is too close to the landing pad, then you're just going to erode the berm. You know, you're going to be blowing dirt up off the lip of the berm, and you actually get enhanced erosion because you're deflecting the gas there. So you're going to be ramping more dirt up at a higher angle. That may be okay. You know, maybe the flux isn't enough that it's going to hurt anything, but we need to think about that. But the other issue is that if you put the berm farther away so that, you know, the gas dynamic pressure is lower, then the berm has to be so tall that it becomes unreasonable. The same problem with curtains. We've looked into just deploying curtains. Andy Abernathy in the crew office was during the Constellation program was a champion of that idea. But trying to put curtains around a landing pad, you're basically putting up sails, you know, like sailing on a sailing ship. So they've either got to be giant far away, or if you put them too close, they're going to fill up with plume gas and blow over. So I'm just a big fan of solidifying the surface, but the surface itself could fail. You could spall it and blow out chunks. And so I think berms are still needed.
Possibly if you could, on the near side of the burn, populate that with large rocks that wouldn't get blown away. I don't know if anybody's looked at that. It makes the process of creating the berm a lot more difficult, though.
Yeah, if you 3D print, like Rob Mueller is working on some of these technologies at Kennedy Space Center, and he's been looking at 3D printing a berm with a solid surface and then shaping the surface to deflect things in the direction you wish. I forgot, I should have mentioned the other issue with berms is that most of the ejecta goes at a low angle, but in the very final seconds of landing in the Apollo landings, we could see a blast that goes at a much higher angle when you get some local shearing of the soil right under the plume when the shear forces get very strong. And so for these much larger landers like Starship and Blue Moon and the Dynetics lander, we don't know yet. We can't predict yet if there's going to be any local failure under the nozzles.
Looks like we have a question from Monchin.
Yeah, I had a question on the kind of concentration of dust in the lunar atmosphere. Is there a level above which it's considered unsafe for a lander to navigate, or unsafe, or like where the visibility is too low to attempt, or is that kind of a play by ear type decision?
In terms of the atmosphere, I guess it depends on what you're talking about in terms of atmosphere. I would say the amount of dust in the actual, the atmosphere is very, very low. It's really just, that it's a visibility issue, kind of those final tens of meters above the surface. I don't know if you have anything to add to that, Phil.
Well, so I know there's a group at the Johnson Space Center that manages the environmental spec for lunar orbit. And I know they've been working on it, but I don't know the outcome of that. I can also add this, that video I show you, which had the ejecta going all around the moon. That was a simpler Kepler's equation calculation. We did not take into account tidal forces or the sun's gravity and the fact that these different gravitational masses are moving around. We didn't take into account the solar wind. So it's possible that some of the ejecta could end up being trapped in cislunar space when you take into account these other forces. And so there is a concern. Josh Colwell is a physicist who's studying, a planetary scientist who's studying this. And so there is a concern that over a lot of landings, you could build up some ejecta in the Earth-Moon system that could start to be an issue for telescopes, for example. Starts to get in, it's orbital debris of a different kind. I don't think it's a big risk, but we do need to look at it to answer if it's a real risk or not. It is a self-correcting risk because eventually the solar wind does blow all that stuff away, but there's a question whether it could build up and have a quasi-stable population of dust.
Yeah, and I think that's kind of what I'm asking about, where when we start to have a lot more landings and there's a lot more ejecta, and kind of how does that impact future landings? And I guess maybe a follow-up question to that is, do you see us reaching a point where like all of that ejecta will form some sort of, or will interact with each other kind of as it gets kicked up and create some sort of storm system, or other sort of surface level or atmospheric level event.
I don't think so. The video is deceptive because the size of a pixel on that is giant, compared to an actual dust particle. So the ejecta sheet was actually very dilute. I mean, at the thickest point, our current models predict that the gateway may have, I forget what the number is, like 1,000 impacts per square meter or 10,000, which sounds like a lot. But when you realize these are 10 to 1 micron dots, the amount of surface area that it interacts with is an extraordinarily tiny amount of surface area. So I think it's such a dilute effect that it needs to be in the environmental spec, and instrument operators need to know about it. I don't think it's a threat to the spacecraft. And I don't think there'll be any secondary physics effects like electrostatic effects or anything inside that cloud. I think it's just a dilute cloud that will eventually disperse because of the solar wind.
Thanks.
Until we have another question from the class, something else I wanted to ask you both is, we do have a project in the course this term that's looking at passive gathering of regolith on rover wheels. I'm just curious, what, if anything, do we not yet know about lunar regolith? What would be interesting to both of you to learn and further characterize lunar regolith?
I imagine Phil will have somewhat similar answers to me, but I would say one of the kind of more immediate interesting things is characterizing regolith properties in these polar regions, because we just don't know a lot. I mean, we've not landed in one before, so we don't know how the colder temperatures and the presence of volatiles affects things like, the porosity or the electrostatics or the compaction. So any of those kinds of measurements would be particularly useful. There are lots of geotechnical measurements that are of interest all over the moon, but that's the one that came to mind first.
Ryan actually did compaction experiments and with thermal cycling, and because there's no thermal cycling at the poles of the moon, or much reduced, it's lacking one of the compaction mechanisms that does operate elsewhere on the moon. So that's interesting work. In fact, I have it on my whiteboard, Ryan. I'm looking at your name on my whiteboard to get back to that topic.
Yeah.
But I'll just add that Carlos Calle at the Kennedy Space Center was developing an electrometer to go on rover wheels. So as you're driving, you're tribocharging little patches of different material on the wheel, and it becomes an electrometry spectrometer. So the different minerals in the soil will tribocharge different materials to different degrees. And by having a variety of materials on your wheel, you're actually measuring a tribocharging series. And so it can allow you to characterize the regolith mineralogy as you're driving. So that would be an interesting thing to consider as well. But I just want to hear that right. What was the name of this course or this topic? I mean, that's fascinating.
Yeah. Absolutely. So yeah, we can give you just a minute maybe of overview about the class. The course name is Operating in the Lunar Environment. Jeff and I are co-teaching.
Oh, no, I'm sorry. I meant the thing about the rover wheel. So that was...
The rover wheels in particular. It's a space-enabled project out of Danielle Wood's lab. Javier Stover is the lead, and I believe our student Kiyohide is the representative for this project. Kiyohide, do you want to say hello and tell them a little bit more about the project? I think you're muted.
Oh, sorry. Yeah. My project is to gather the regolith by using the passive regolith collection system, and this method is to attach the add the attachment to the whole surface. And also, we will use wax to paraffin wax to catch the regolith. So our project will be contribute to understand the character of the regolith on the surface of the moon, I think. Yeah. So, and also I'm interested in the the polar surface on the moon of the regolith. because because the polar area is not affected by the sunlight, so it might be different from the other. It might be different from other areas. So I think that our project might be might be able to explore the character of the regolith, on the porous area, I think. Yep.
So Tony Colaprete, who was the PI on the L-Cross mission, was telling me that I don't think they ever published this. I mean, it's sort of barely mentioned in one sentence in one paper, but when the L-Cross impacted, there were two ejectocones. One was broad and shallow, one is steep and narrow. And also there was the visible flash of impact was absent. It was suppressed. And the infrared flash was delayed, I think 300 milliseconds, 200 milliseconds. And the only way they could repeat this in small scale experiments was if the target soil had 70% porosity to a depth of 2 or 3 meters, which is kind of unbelievable because the lunar soil gets compacted within 30 to 50 centimeters in all the sites that we visited. So how could it stay so extremely porous to such a depth? So that does imply there's something going on there in that polar soil. One possibility is that there is some weak cementation from the existence of the frozen volatiles, and that weak cementation is stabilizing it in a more porous state so that the normal compaction processes are not as efficient. But it's really, we don't understand the physics well enough to try to model that yet, to try to predict that behavior. At least I've never seen any papers yet that have successfully predicted that. And also the data that we have are kind of sketchy. We don't know for sure that it was really that porous to that depth. But yeah, there's definitely a big need to understand that soil in that region.
Wonderful.
Makes me wonder, if you had enough water available, could you just pour a lot of water over a porous landing site and have it freeze and possibly cement it? You might have to refurbish it for every landing, but we use lots of water every time we launch. So just an idea.
Yeah, so we looked at that for Mars. Actually, I've never thought about it for the moon. But so the issue is that about half the water will flash evaporate, but as it evaporates, the faster molecules leave first, right? So you're losing energy faster than you're losing mass. And so you end up freezing about half the water in place. So you're right, it would freeze a landing pad. But then you could Zamboni it, drive back and forth and pressure anneal it into a solid surface. So that is possible. It's a fun idea.
Lots of experiments to be done on the moon, it seems to me.
Oh, yes.
We're only just getting started.
Mm-hmm.
Interesting.
With this,
Well,
we
we're
usually let the
approaching
class.
11 o'clock, and we've got to, unfortunately, end the class. But many thanks to our speakers, to Kevin and Ryan and Phil. And I think, once again, you've shown us how much interesting stuff there is to be done on the moon and how much we still have to learn to make our operations possible. And hopefully that'll give the students some, a lot of inspiration in some of the things that we ought to be looking at in the future, whether for this class or subsequently. So thanks again for taking the time to talk to us. And we'll look forward to more exciting stuff with CLIPS and other lunar activities. Thanks.
Good to see
Thanks
you
for having
all.
us.
Looking forward to some cool payloads.
Yes.
All right.
Bye-bye.
Bye, everyone.